Today I would like to walk you through using your calculator to complete pH and hydrogen ion concentration calculations for those values or times when you don't actually get a whole number to work with, like we just did in our pH lab. So as a way to recall, when you have a hydrogen ion concentration, it means that you have an acid in your solution. And we often want to represent this in a more simplified way. So what we will often do is we will often calculate what's called the pH of your solution. And this is just a whole number that represents something of the concentration or the amount of hydrogen ions present in solution. Now, if you have an acid or a base, you will always have some amount of both hydrogen ions and hydroxide ions present. So if it's an acid, you have a lot more hydrogen ions. If it's a base, you have a lot more hydroxide ions. If you have water, you have equal amounts. We say that it's neutral because they both have the same amount of acid and base ions present. So much like you can calculate pH, you can also calculate pOH of a solution. And today the goal is just to go back and forth between concentration and the P scale, or the scale that makes these into whole numbers that are easier to work with. We will also work our way between these two types of ions. So if I know pH, I could figure out pOH and vice versa. Or if I know the concentration of hydrogen ions, I could also then determine the concentration of hydroxide ions present in solution. So as a couple of things to note here, we're just going to put some relationships out here. So pH plus pOH will always add up to the whole number of 14. And then if you take these two concentrations and you multiply them together, they will always multiply to 10 to the negative 14. And you should notice the symmetry here. Negative 14 as an exponent and 14 on the line. This is the whole goal of determining pH or pOH, is it's taking that exponent value and bringing it down onto the main line together. So we're going to work our way today practicing going back and forth across here, and then also maybe finding out some information about the other ion as it's helpful to us. So when you're working with a hydrogen ion concentration, let's say we had a pH in our lab for a bottle of Coke of 3. What this tells me here is that the hydrogen ion concentration in the bottle of Coke is 1 times 10 to the negative 3 molar, where the pH value here is a logarithmic function, or more simply what it does is it takes the number that's the exponent and brings it down onto the main line as a whole number. What we can do with this then is we can also calculate the pOH of this solution. If I know that they have to add up to 14, then the pOH of my solution is 11. Or the hydroxide ion concentration in this bottle of Coke is 1 times 10 to the negative 11 molar. This means that for a bottle of Coke it is very acidic because it contains a significantly higher amount of hydrogen ions compared to hydroxide ions. So these two numbers add to 14 and these two numbers multiply to 10 to the negative 14. One thing that can be confusing for people is this negative sign, where usually as the exponent gets bigger, it means the number is bigger, but because there's a negative sign here, it actually means that the number is getting smaller. This is 0.001 molar, and then this is got 10 zeros in front of that 1. So this one is much less concentrated compared to that one. So what I'd like to do with you today is I'd like to just practice these calculations with you using your calculator for when you have values that are not whole numbers. So let's take a look at this one. If I have a hydrogen ion concentration of 2.0 times 10 to the negative 8th molar, I would like to determine its pH value. I actually don't have a way to do this directly just by sight. I could estimate here that my pH value should be pretty close to a value of 8. This is just a little bit basic, but what's complicated about this one is that it has a number out front here, and it's not just 1 times 10 to the negative 8th. So this will end up being a pretty good estimate for us, but now we want to use our calculator to actually apply the logarithmic function to this value to come up with a more precise number. So when we're working with our calculators, the button that you're going to look for every time for these questions is this log button right here, LOG. LOG, or the log button, what it does is it takes this 10 with the exponent and it breaks it apart. It pulls that exponent down onto the main line. And so this log button is going to be important for us. And this is what you're going to use for all pH calculations. In general, the way that we're going to write this is we're going to say that the pH of any substance can be calculated by taking the negative log. So I'm going to press the negative sign and then log of the hydrogen ion concentration. So I'm going to break down this base number of 10, and then I'm also going to apply a negative sign to it so that this exponent becomes positive. So let's look at that calculationally. What I'm going to do with this here is I'm going to apply a negative log. It needs to be the negative sign, not the subtraction sign. And then I'm going to plug in my number, 2.0 E negative 8. And remember, our value here should be pretty close to 8 because that's what the exponent is, but this 2 out front is going to bump it a little bit away from 8. So I come up with a number here of 7.7. So our value of 8 is actually a pretty good approximation of this, but we can use our calculators to get closer to the mark. So again, if you have a number with an exponent in it, it means that we want to get rid of the exponent by applying the negative log. You can also go the other way. So instead of pulling the exponent down, what if we want to put the exponent back up there? So this would be going from the pH value to the hydrogen ion value. So we have a pH value of a solution is 2.5, and I want to know what's the hydrogen ion concentration of this. Well, remember, if I had a pH of 3, then it told me that my hydrogen ion concentration had a concentration of 1 times 10 to the negative 3 molar, where you're taking this and putting it back up into the exponent. So mathematically, we will do the same thing. So if I am calculating the hydrogen ion concentration from my pH, I need to, instead of pulling the exponent apart, I need to put it back together. So I'm going to do the inverse function of a log. The nice thing about your calculator is that it will always put the two functions that are inverses of each other on the same button. So you'll notice x squared, so squaring something, shares the same button with the square root, the thing that undoes that square. For the log button, you have LOG on the main key, and then above it you have this value of 10 to the x. And what that's going to do is it's going to take this 2.5 value and put it back up into the exponent and calculate it for us. So if I'm coming up with the hydrogen ion concentration of a solution, I'm going to do 10 to the negative. Remember, these numbers are always very, very small, and we need to put the negative sign back in there of the pH number. So if I want to know what the pH, what the hydrogen ion concentration is for a solution that has a pH of 2.5, I'm going to take not the log button, but I'm going to take second log. You'll notice it's now a 10, and it's got a blinking exponent space for us to plug in our numbers. I'm going to do negative 2.5. And that gives us a number here. If I put it back into scientific notation, I'll put 3.2 times 10 to the negative 3. This does have a unit on it. It's molarity for concentration. And you'll notice here that 3 and 2.5 are pretty close to each other. But the fact that we don't have a whole number means that this front number will not be able to be a 1. It'll bump around a little bit. So if we're trying to make some calculations here, then you're going to use this log key, and you're going to use it either to deconstruct the exponent or to put it back together, depending on what direction you're going between. Okay. Now, as a last thing, you might also be asked to determine something about the pOH, or the hydroxide ion concentration in solution. So I have a solution here that has a hydrogen ion concentration of 3.1 times 10 to the negative 4. So if I wanted to estimate my pH value, I'd say it's probably pretty close to 4. And that means that my pOH would be pretty close to 10. And then I could also calculate my hydroxide ion concentration. Let me refocus my camera here. Okay. But let's do some calculations. Now, the way that I would prefer to calculate this, or the way that I find it easier, is to say, let's calculate pH first, and then I could go to pOH and hydroxide ion concentrations, because this is just an addition. It just adds up to 14. Whereas if I'm trying to solve for this using 10 to the negative 14th and dividing, I find that it's easier to make errors with my work. So I'm going to solve for pH first, and then I'm going to work my way around to this hydroxide ion concentration. So to calculate pH, I'm going to take the pH is equal to the negative log, because remember I need to pull this exponent apart, of 3.1 E negative 4. And I'll plug that into my calculator. So I'm going to do the negative log of 3.1 E negative 4. Okay. And I end up with a value of 3.5. If you get a negative value, it means that you forgot to multiply on that negative sign out front. pH values and pOH values, at least for our class, will always be positive. Okay, and that's pretty close to what we estimated. Then if I want to know what my pOH is, I'm just going to subtract away the pH from 14. So I'll take 14 minus my answer, and I'm left with 10.5 for my pOH. As a last step then, if I now know my pOH, I could do the reverse of the log to get to hydroxide ion concentration. So if I have my pOH, and I want to go to concentration of hydroxide ions, then I need to do the inverse of that log function. So remember, I'm going to determine this by doing the 10x button, so 10 to the negative pOH. So I still even have this in my calculator, so I'm not even going to undo it or retype it. I'm just going to do second log negative answer. And I end up with a value of 3.2 times 10 to the negative 11th molar. Which again is fairly close to our approximation, though it's not exact. Okay, so this is my third step here. So again, as we go back and forth between concentrations and what's called the p-scale, we're either trying to bring this exponent, down onto the main line to make it an easier number to work with. Or if we know the pH of a system, or if we know the pH of a material, sometimes we might want to actually figure out what is the actual concentration then of my particular species. Is it for hydrogen ions or hydroxide ions? So we can go back and forth between the two, either pulling that exponent down onto the main line or putting that large number back up into the exponent to come up with a genuine value. I hope this helps.